Swayam Prabha. Digital India. Educated India.
So, hello everyone, welcome to the class on pericyclic reactions. So, today's topic is sigmatropic reactions. Yeah, so sigmatropic reaction is also a type of pericyclic reaction. So far in the previous classes, we have discussed two different types of pericyclic reactions. One is the electrocyclic reactions and the other is the cycloaddition reactions. So this is the third type of the pericyclic reactions and it is named as sigmatropic reaction or sigmatropic rearrangements. Okay. So the name is suggesting us something. So if you look at the name, it is saying like sigma and tropic. So first of all, let us see this new term, so that is tropic. So tropic refers to movement or migration. So tropic is nothing but movement or migration. So what is being moved or what is being migrated is the sigma bond. So together a sigma bond is migrating, sigma bond is moving from one place to the other place. Now the other term we are using here is sigmatropic reaction or rearrangement, right? So what do you mean by rearrangement? So rearrangement is nothing but arranging something within the given place. So a sigma bond is breaking at one point and then migrating to the other point of the same molecule and then forming a new sigma bond. So this is the entire very clear and small concept of the sigmatropic rearrangement reactions. So a sigma bond is being broken down at one point of a molecule and then it is migrating to other end of the molecule and then it is forming a new sigma bond there. So this is nothing but the sigmatropic rearrangement reaction. We can say like if one of you who are occupying these desks in the class is moving from the one desk to the other desk or in a different row, it is called as rearrangement, because as a whole the number of students in the class is not changing. Similarly, in a rearrangement reaction, the molecular formula or the molecular weight will not change. Only the atoms or groups will be migrating or changing the positions from one place to the other place within the same molecule. Okay. So now if I am taking the class here, if I move out of the class and someone else is coming in my place, so that is called as substitution reaction, right? If 2 or 3 in the class, they want to go out of the class, so that is nothing but elimination reaction, okay, completely if they are moving out. If one is moving from this class to the other class, it is called as transfer reaction, okay. So transfer. So this is the common terminology which helps you to understand very easily how the reactions are. So sigmatropic rearrangement is nothing but the movement of a sigma bond from one place to the other place of a molecule in a concerted manner is called as sigmatropic reaction or rearrangement process. So how do you define the sigmatropic rearrangement reactions? So it is the breaking of the sigma bond. If any reaction is involved in the breaking of a sigma bond followed by migration of that sigma bond in the pi center, along the pi center of a system is called as sigmatropic rearrangement. So how it is happening? For example, if you have a molecule like this where an atom or a group is there, so this particular sigma bond, if migrating from one place to the other place like this, so previously the sigma bond which is intended to migrate is here and now it is seen here, right. So this is nothing but a sigmatropic rearrangement reaction. In a proper way, if you want to define the sigmatropic rearrangement, it is nothing but the reactions which are involving the breaking of a sigma bond and migration of that particular sigma bond either with or without the groups or atoms attached to it. It is called as sigmatropic rearrangement reaction. Similar to all other pericyclic reactions, sigmatropic rearrangement reaction is also follows the concerted type of mechanism. That means the reorganization of the pi electrons, breaking of the sigma bond and formation of a new sigma bond at the end of the pi bond is happening simultaneously in a one shot. So, it is a concerted type of mechanism. So, all the sigmatropic rearrangement reactions similar to other pericyclic reactions also follow the cyclic transition state. So, you cannot see any formation of the intermediates. So, all these reactions will pass through a cyclic transition state where the breaking of the sigma bond and reorganization of the pi electrons as well as the formation of the new sigma bond takes place simultaneously. So, how does these sigmatropic rearrangements are notated? So, if someone has to notate a sigmatropic rearrangement, so they have to give the order of the reaction with two numbers. So, they have to give the order of the reaction with two numbers. Coming to the example which we have discussed earlier. So, if this is the sigma bond and now you have to select a sigma bond which is migrating, right. So, the sigma bond which starts at the saturated carbon atom. So, these two are the unsaturated carbon atoms, this is the saturated carbon atom, that means N_sp3 carbon atom, or this can be an allylic carbon atom also, okay. Or you can also say like this is the alpha carbon atom to the unsaturation, this is the unsaturation and this is the alpha carbon atom. The sigma bond which is attached to either alpha carbon atom of the unsaturation or the saturated carbon atom next to the unsaturation, or you can say like the allylic carbon atom should be given numbering like the first one. So, 1, 2, 3. The other end of the sigma bond should also be given the numbering. So, it is sensing like the sigma bond which is migrating is in between 1 and 1 position. So, after the sigmatropic rearrangement, so it will move this way, right. So, double bond is here. So, now you look at the numbering of this system or the reaction. So, it is notated or the order of the reaction is shown in two numbers like 1, 3. That means the sigma bond is moving from position 1 to position 3, which is the termini of the unsaturation, So, therefore, the numbering should also continue until the end of the unsaturation. For example, so if this is the molecule which is undergoing the sigmatropic rearrangement, the numbering should start from here 2 and 3, it should end here only. No need to consider the extension, these are not continuing the pi bond, okay. Or if there is one more double bond here, then the numbering should go until here, okay. So, the numbering should start from the saturated carbon atom which has a sigma bond migrating in the reaction to the end of the unsaturation. Now, the sigma bond will move to the termini or the end of the unsaturation. We call this as order of the sigmatropic reaction, If you look into this example where A is connected to B and B and C are connected to each other via a double bond. So, now this is the unsaturated part of the molecule. If A is connected to M is nothing but a migrating atom or a group, right. So, M is a migrating atom or a group, right. So, this sigma bond will slowly move to the other end of the pi bond, whereas this pi bond will be moving in this way. So, what you will be seeing at the end of the reaction is A connected to B via a double bond and now C connected to the migrating group. So, the place where the bond is getting broken is called as migration origin. So, the place where it is moving is called as migration terminus. So, if you label the carbon atom, so then you can know the substituent or the group or atom which is holding the sigma bond or which is intended to migrate from one place to the other place has really migrated or not, can be confirmed by labeling of the molecule, right. So, any extension in the unsaturation. So, if I extend this further, now the molecule is providing another option for this migrating group or atom along with the sigma bond to have a new position, whether either it can go to the C or it can go to E, right. So, the number of electrons involved in this particular sigmatropic shift can be calculated easily by just doubling the number of arrow marks shown, right. So, how many arrow marks are shown for the 1,3 shift means, so this is 1 and this is 2. So, therefore, 2 into 2 will be 4 electrons. So, this category falls under 4 electron system of a sigmatropic rearrangement, right. So, if the migrating group is moving from here to here, now one more pi bond can get into the things, right. So, now 1 arrow mark, 2, 3. So, how many electrons are involved? Both sigma as well as the pi electrons involved in this type of sigmatropic reaction means 6 electrons. So, it can be categorized as 4n plus 2 electron system of a sigmatropic reaction. So, therefore, you can get this product as well as there is every possibility of this one, right. This is 4 and this is 5. So, therefore, this comes under the category of 1, 5. So, this comes under the category of 1, 3 type of sigmatropic rearrangement reactions. It is absolutely necessary to understand the type of sigmatropic reaction depending upon the origin position as well as the termini position. So, that is the ending position. Migration origin as well as the migration termini will give us a understanding of where it is starting and where it is ending. So, based on this, all the sigmatropic reactions are ordered in the two different types. One is 1, j form and the other is I, j form. All the sigmatropic reactions are categorized into two types. One is 1, j type of sigmatropic reaction. So, the other is I, j type of sigmatropic reaction. So, what is the information you can immediately collect over looking at these two types is 1, j means one end of the sigma bond is having a fixed position. So, as sigma bond is having two ends, one end is only changing and getting a new position which is symbolically represented as j. So, j is nothing but a new position. So, whereas the other type I and j both are different, right. So, that means the sigma bond is entirely changing both the ends. So, both the ends are now getting the new positions. Therefore, they are categorized as I, j type of reactions. So, the same example which we have discussed previously, if you have this carbon skeleton and one sigma bond connecting the migrating atom or group is there. So, the numbering should start at the saturated carbon atom, right. So, here this is the saturated carbon atom. So, or the one of the ends of a sigma bond, which is highlighted in the thick line, right. So, you start here as 1, this is 2 and this is 3, third carbon atom. So, the other end of the sigma bond should also start with 1. So, this is 1. So, this is called as migration origin, and the place where it is relocating, it will be called as migration terminus, right. So, what is happening here is the sigma bond along with this atom or group is moving this way, and therefore, this pi bond is relocating here, and the product is like this: C double bond C, single bond C and M. So, if you look at the numbers, so this is the first one, second and third one labeled as that. So, and this is the 1. So, previously the location of the sigma bond is in between 1 and 1. So, now the location, new location is between 1 and 3. So, therefore, such type of sigmatropic reactions are labeled as 1, 3 in square brackets. So, in the square brackets, so on the arrowhead you have to mention like 1, 3 sigmatropic reactions. So, if in any type of question, if the reactant is given on the arrow, if they mention 1, 3 or 1, 5 or 1, 7 or something like that, so you should clearly understand that this particular reactant molecule upon thermal irradiations or photochemical irradiation is subjected to a sigmatropic shift, and therefore, the new position is given in the bracket, right. So, that you have to understand from this notation. Okay. So, this is 1, 3. So, similarly, if number of carbon atoms is more, one more pi bond is there. So, therefore, you can see 1, 5 also, right. If one more pi bond is there connected to it, extension of another pi bond, so you can also see 1, 7 type of sigmatropic rearrangement. In all these cases, one thing is pretty sure, like one end of the sigma bond is fixed, right. So, the other end is only changing, whether it is going to the third atom or fifth atom or seventh atom, it is a different issue, but the one end of the sigma bond is constant, right. So, these are called as 1, j type of sigmatropic rearrangements. So, in other case, both the ends of the sigma bond is changing. You see this interesting example. So, if A, B connected to C via a double bond, and similarly it is connected to this, right. So, the sigma bond which is migrating is this one. So, how the numbering should be? It should start from here 1, 2, 3 on this end of the sigma bond. Similarly, it should start from here 1, 2, 3, right. So, upon sigmatropic rearrangement, what you will get is this one, right. So, what is the numbering here? 1, 2, 3, 1, 2, 3. See now, the new location of the sigma bond is in between 3, 3. So, that means both the ends of the sigma bond has changed. So, such type of reactions are denoted as 3, 3 sigmatropic reactions. There are some more examples which are proved. You can see like 2, 3 type of sigmatropic reactions, 1, 4 type of sigmatropic reactions, 4, 5 type of sigmatropic reactions, and 5, 5 sigmatropic rearrangements. So, different types of sigmatropic reactions are possible depending upon the migration origin position and the migration termini position. So, so now we need to think like how this is going to happen. So, as in the case of all other pericyclic reactions which we have discussed earlier and which we will be discussing in the future, so all the pericyclic reactions will happen via a cyclic transition state in a concerted manner. So, as the sigmatropic reactions are also. So, we will see how it is going to happen. If this is the carbon skeleton and this is the atom or the group attached to the carbon skeleton, right. So, numbering is like this 1, 2, 3 and this is 1. So, upon sigmatropic rearrangement, that is 1, 3 type of sigmatropic rearrangement. So, what is happening here is slowly the sigma electrons here are moving to this carbon atom. Therefore, one of the pi bonds here is slowly delocalizing here, right. So, this sigma bond is slowly breaking down. So, what you will see in the cyclic transition state means the sigma bond, existing sigma bond slowly vanishing, a new sigma bond is forming in a different termini, different position, and then the pi bond is relocating, right. So, this is the cyclic transition state you can observe during the sigmatropic rearrangement. So, the end product is this one 1, 2, 3. So, previously the pi bond is in between 2 and 3 carbon atoms, now in the product it is in between 1 and 2. Previously the hydrogen atom or the group with the sigma bond is connected to the carbon 1 and now it is at the carbon 3, right. So, this is the brief mechanism for the sigmatropic reaction. Any sigmatropic reaction will follow this kind of cyclic transition state and then evolve into the product. So, now we have to discuss about the stereochemistry of the sigmatropic reactions. Before the starting of this course, from the first class, we have been communicating to each other like, so sigmatropic, not only sigmatropic reaction, any kind of pericyclic reaction are highly stereospecific in nature, provided fixing the reaction conditions. If you fix a reaction condition, a particular reactant molecule will always give you a particular stereo product, stereoisomeric product, right. So, you will not get a mixture of these products. So, based on the reaction condition, a particular reactant is always going to give you a particular product. That means, you can estimate the type of product, the stereochemistry of the product well before starting the reaction, depending upon the reaction conditions and the stereochemistry of the reactant molecule, right. So, in electrocyclic reactions, how it is happening, in cycloaddition reactions, how the stereochemistry is happening. So, that all we have discussed thoroughly. Now, in order to discuss the stereochemistry of the sigmatropic reactions, one thing first we need to understand is, so it is the migration of a group or atom from one place to the other place of a pi molecule, right, conjugated unsaturated molecule. So, unsaturated molecule with the double bonds conjugation gives you a planar shape. The planar molecule sp2 hybridized carbon atoms will give a planar or shape, right. So, that means, if you see that this is the sigma bond which is connected to the unsaturated system, right, and holding an atom or a molecule, if you consider this as an atom or a molecule, and now it has two options now. It can simply break the sigma bond here and then go to the end like this, right. So, that means, it is not changing the phase of the pi center, pi system. So, from lower phase, it is slowly migrating to the other end in the lower phase itself, right. Or if this is the sigma bond and the atom or group connecting the other end of the sigma bond is on the top phase of the unsaturated system, now it is breaking the sigma bond here and then slowly going to the other end, right. In both the examples, what you can observe is, it is not changing the phase of the pi system, right. So, from lower phase it is going to the lower phase, from upper phase it is going to the upper phase. If such is the case, So, we call such kind of sigmatropic reactions as suprafacial. We call them as suprafacial sigmatropic reactions. So, now if this sigma bond is connected to the pi system this way and it has to migrate to the other end, but what it is doing is breaking the sigma bond from here, which is on the lower face, and then crossing the pi system and then reaching the upper face of the pi system. You observe here now, it is on the lower face in this corner, and then now it is breaking down here from the migration origin and then crossing the pi system. This is the pi system, right? So, it is crossing the skeleton of the pi system and then reaching the upper face, from lower face to upper face, or from lower face to the upper face to the lower face is also same. Now, it is crossing the system, pi system. So, such kind of migration is called as anterafacial sigmatropic reactions. So, now the stereochemistry depends whether the migrating sigma bond is following the suprafacial mode of migration or anterafacial mode of migration, right. So, if carbon skeleton is like this, so this has two faces now, one is lower face and this is upper face. Okay. So, the migrating sigma bond is connected this way. If the migrating sigma bond is moving from the lower face to the lower face, it is called as suprafacial. If the migrating sigma bond is crossing the carbon pi center, pi system, and then moving to the upper face, so now it should be called as anterafacial mode of sigmatropic reaction. So, you can see here clearly. So, it has crossed the pi system, right. So, this is anterafacial mode of sigmatropic reaction. You can see this way also 1, 2, 3. So, now if this is moving from lower face to the lower face, in the cyclic transition state, what you will see is this kind of in cyclic transition state. Later, once the product is formed, you can see still the migrating group on the lower face itself. So, this is called as 1,3 suprafacial, 1,3 suprafacial sigmatropic rearrangement. So, now if this is the system which is subjected to sigmatropic rearrangement, but during this the migrating group is crossing the pi system in the cyclic transition state. You can see this way, and therefore, the product will be like this. So, the migrating group is on the upper face. So, it is on the upper face now, it is on the lower face, similar to that of the reactant, right. So, these are the two different types of approaches or stereochemistry you can see during the migration of the sigma bond. One is suprafacial mode and the other is the anterafacial mode. Now, it is time to deal with the analysis of the sigmatropic reactions. So, when we started analyzing the other pericyclic reactions, that is the electrocyclic reaction or the cycloaddition reactions, we always had three options or three methods, different methods to analyze the pericyclic reactions. So, one is orbital correlation method, right, and the other is frontier molecular orbital approach, which is called as FMO method, and the other is transition state aromaticity method, right. So, these three methods, any of these three methods could possibly or easily help us in analyzing the electrocyclic reactions or cycloaddition reactions, which we have discussed in the previous classes. But now coming to the sigmatropic reactions, there is a small issue. So, what is that means? Majority of the molecules which are undergoing the sigmatropic reactions will not have any kind of symmetry elements, either in the reactant form or in the product form. They may have these elements of symmetry in the transition state. So, if they are not having or not showing any kind of symmetry elements, either in the case of reactant or in the case of the product, so it is highly impossible or difficult to use the orbital correlation method for the analysis of a particular sigmatropic reaction, right. So, there is, of course, there is an exception of n, n type of sigmatropic reaction, which is also called as 3, 3 type of sigmatropic reaction, right. So, there is an exception for that, but in general for any kind of sigmatropic reaction, it is difficult to use the orbital correlation method for the analysis. So, what are we left over with? Means we have two more methods. If orbital correlation method is not going to help us, not an issue. So, we do have two different types of methods, which is frontier molecular orbital theory method, that is FMO method, and the other is the transition state aromaticity method, right. So, but as per the rules proposed by the Woodward and Hoffman, the frontier molecular orbital approach has to consider these systems, this pi system, in order to develop the pi molecular orbitals. How do we do that? Means Woodward and Hoffman started assuming that the sigma bond which is migrating from one termini to the another termini is undergoing homolysis, So, what if any bond undergoes homolysis? We will get free radicals, exactly, right. So, now they are considering the homolysis, they are assuming the homolysis of the sigma bond that is migrating from one place to the another place, and based on that they have started constructing the molecular orbitals, pi molecular orbitals. So, therefore, always you will be seeing in the case of sigmatropic reactions the odd number of carbon atoms involved, So, during the construction of the pi molecular orbitals in the previous class, we have not considered the pi molecular orbitals for any odd numbered centers, carbon centers, right. So, now it is time to revisit them and then develop the pi molecular orbitals for the odd number containing things, right. So, what is the least odd number containing system, pi system, which can participate in the sigmatropic reaction? Means it is allyl radical, that is what we will get, right. So, if this is the pi system and this, according to Woodward and Hoffman, the migrating sigma bond is undergoing homolysis, the resultant you will be seeing is a radical, which is nothing but allyl radical having 3 carbon atoms, So, now we will try to develop the pi molecular orbital for this. So, psi 1, psi 2 and psi 3, 3 pi molecular orbitals will be formed, will be seen here, because 3 carbon atoms are involved, right. So, please try to recollect what we have discussed in the previous classes. So, psi 1, the number of nodes should be 0, because n is 1 here, 1 minus 1, that is n minus 1 is 0, 0 number of nodes should be there. Therefore, it will be having the wave functions in this way, right. There is no chance of any node, it is completely bonding. So what you will get for this is sigma plane of symmetry. So you will have a sigma plane of symmetry and C2 axis of symmetry is absent here. Coming to psi 2, the number of nodes here is 1. That means one node will be certainly there. So and now it will not have the sigma plane of symmetry, it will surely have the C2 axis of symmetry, right. So therefore the wave functions will be like this, plus minus. So the entire this orbital will become the node for this. Coming to psi 3, number of nodes will be 2. These are nodes and this is sigma plane of symmetry, and this is C2 axis of symmetry, right. So number of nodes will be 2 and it will have a sigma plane of symmetry and it will not have C2 axis of symmetry. So number of nodes is 2. So therefore the nodes will be appearing in between these orbitals. So plus, minus and plus. So this is the pi molecular orbital which you can see for the radical system, allylic radical system with 3 carbon atoms, right. So the exact pi molecular orbital will be there for an allyl carbocation as well as an allyl carbanion. Only difference here is, in order to analyze the reactions with the frontier molecular orbital theory, you need to know which one is HOMO and which one is LUMO. So HOMO will be different under thermal conditions and different under photochemical conditions. For example, if psi 1, psi 2, psi 3 are there, their configuration, electronic configuration is like this. Psi 1 will have 2 electrons, psi 2 will have 1 electron and psi 3 with 0 electron, right, because this is a radical, 3 electrons will be there, right. So 2 occupies the psi 1 which is the bonding and psi 2 1 electron will be there. So therefore if you see the energy profile, so this is psi 1, psi 2 and psi 3. Under thermal conditions, HOMO is selected in ground state, right. HOMO is in ground state. So the occupancy of electrons is like this. Psi 1 will have 2 electrons and psi 2 will have 1 electron, psi 3 will not have any electron. So now which one is the HOMO? Yes, psi 2, right, very good. So psi 2 becomes HOMO molecular orbital under thermal conditions, right. So if you move on to the photochemical conditions for the same system, so what will happen in the photochemical condition means, an electron from the ground state will move to the first excited state. After irradiation, it moves to the first excited state. So therefore under photochemical condition, this electron has moved to psi 3. There is no more electron in the psi 2 under photochemical conditions. So it has moved into psi 3 because you will be selecting HOMO in the first excited state. Yeah, so now psi 3 has 1 electron under first excited state. So therefore under photochemical condition with the same system, psi 3 becomes the HOMO molecular orbital. Psi 3 becomes the HOMO molecular orbital. Quickly we will see the pi molecular orbitals for 5 carbon systems, that is with extended conjugation. Yeah. So if this is the reactant molecule, which is, subjected for the sigmatropic reaction according to Woodward and Hoffman, you need to consider that the sigma bond is undergoing homolysis. So, the resultant of this is a radical, right. What is this? Pentadienyl radical. So, this is pentadienyl radical. So, how many carbon atoms are there in this system? 5 carbon atoms. So, how many molecular orbitals we will be expecting? 5 pi molecular orbitals, right. So, what will be the configuration? We will see. So, psi 1, psi 2, psi 3, psi 4 and psi 5, 5 pi molecular orbitals will be formed. So, electronic filling will be this way for the radical, pentadienyl radical. If it is pentadienyl cation, you cannot see this electron, right. So, that will be the electronic configuration. If it is pentadienyl anion, you will see 2 electrons here. So, as of now we are discussing about the radical system. So, therefore, 1 electron is there in the psi 3, right. So, the energy profile if you see for these pi molecular orbitals, psi 1, psi 2, psi 3, psi 4, psi 5, right. So, psi 1 number of nodes is 0, it will have sigma plane of symmetry and C2 axis of symmetry is absent, right. So, therefore, you will get to see this kind of wave functions, there is no node at all. Psi 2 will have one node, it will not have sigma plane of symmetry, it will definitely have C2 axis of symmetry. So, therefore, plus plus. So, the entire orbital will become the node, minus minus. And now, psi 3 will have 2 nodes, sigma plane of symmetry and no C2 axis of symmetry. So, now you see plus how many nodes should be there? 2 nodes, minus and this becomes the node and plus. Psi 4 will have 3 nodes, no sigma plane, but C2 axis is present. So, how it will be? Plus a node will be there, minus, and this entire orbital will become the node and plus a node again and minus. And this one psi 5 will have 4 nodes, sigma plane and no C2 axis of symmetry. So, plus minus plus minus plus. So, everywhere you can see the node. Okay. So, this is the pi molecular orbital for the pentadienyl radical system or pentadienyl cation or pentadienyl anion. So, in the ground state, which one becomes the HOMO? Under thermal conditions, you see, under thermal conditions in the ground state you choose the HOMO, right. So, which is HOMO now under ground state? Psi 3 becomes the HOMO, psi 3 becomes the HOMO. In the first excited state, that is the photochemical conditions, the configuration is, I will write here, psi 1 2, psi 2 2, psi 3 0, psi 4 1 and psi 5 0, right. One electron from psi 3 has moved to psi 4 in the first excited state. So, therefore, this becomes the HOMO. So, these are the things. So, keeping in this mind, we will start analyzing the pericyclic reaction, that is sigmatropic reaction, in the next class. So, thank you so much for your patience.